Hello, my name is Antonio Reid. I'm here with Dr. James White. Dr. James White is the professor of paleoclimatology and climatology at the University of Boulder, Colorado. His research is done in the Institute for Arctic and Alpine Research. Dr. Jim White, can you tell us a little bit about your studies in paleoclimatology and how paleoclimate relates to the current episode of climate change we are experiencing today?
My work in paleoclimatology has been primarily in ice cores, but I've also worked in using tree rings and lake sediments. There are many places on the planet where information accumulates over time. And like the pages of a book, if you go back and read through what happened in the past, you can get some idea of what the planet is capable of from an environmental point of view. Not just climate, but changes in vegetation, changes in sea level. There's a bunch of things that have changed on our planet. What's important to understand when you study the history of the Earth is that we live on a very dynamic planet, that we have temperature changes, that we have very large sea level changes, we have very large changes in precipitation. This is an interesting lesson for us because as human beings, we tend to think of things as being sort of stationary and predictable. And they may be predictable, but they're certainly not stationary. So for example, one of the things one learns from the paleoclimate record is that temperature changes on our planet are not all that big. So in the last 40 million years, for example, we've had ice ages and we've had no ice at all on land. It's been very, very warm. And the temperature has dropped by about 6 degrees over that time period, 6 degrees C, when it was the coldest of the cold times. And it went up by about 4 degrees C during the warmest of the warm times. And so there's about a 10 degrees C dynamic range, if you will, in temperature on our planet over that last 40 million years. Yeah, go ahead, Antonio.
Dr. Jim White, I wanted to ask, on your bio page, you say that temperature shifts of 10 degrees Celsius are quite common in the paleo record occurring within a human lifespan. Can you talk a little bit more about that?
Yeah, so I was going to loop into that. So so what I'm telling you is the 10 degrees C is sort of the mean annual temperature, right? And it's important to recognize, however, that there are parts of the planet. So locally, temperature changes can be very large. We know that from season to season. We know that, and less so from year to year. But our planet has, rather than go through calm, progressive kind of changes, our planet tends to have thresholds. So it'll cruise along in a cold state, and then it wants to be in a warm state, but it'll sort of accumulate energy, and then boom, up it goes to the next state. It's more of a, if you think about the old model of the atom, we used to think about where the orbits of the electrons, and they were only in certain places, which is, you know, the model we think of when we think of the atom. That's kind of the way that you can think of climate, that there are states, that it's not every temperature state is possible, but that the planet tends to prefer states. Now, I would point out that mean annual temperatures, that's the whole globe, and that's going to be, that means that locally things can be much larger temperature-wise in terms of changes. So 10 degrees C in Greenland, for example, or 10 degrees or maybe 5 degrees C in North America, these are definitely possible, and they have happened many, many times in the past, very rapidly. Far less than a human lifetime. As I tell my college students, less time than it takes to get through college, because it takes them 4 or 5.
I want to clarify that point, just so I make sure that we're hearing you correctly. You're saying that not only is it possible, it has happened many times throughout Earth's history, that global average temperature has risen 10 degrees Celsius.
Not global average, local. So the Greenland temperatures.
Okay.
Greenland is not global average.
Yeah.
That's important. When paleoclimatologists fan out across the world and start measuring everywhere, then whatever we notice that some places may warm up much faster than other places. There is very much what we call an Arctic amplification or a polar amplification. The poles tend to warm up about 3 times more than the equator does, and that has to do with moisture in the air and a whole bunch of physics particularly the feedback mechanism that when you trade white snow for blue ocean, you are very much changing the energy balance of an area. And so the Arctic tends to have amplification. Having said that, however, it's important for us to recognize that when climatologists like myself talk about mean annual global temperatures, there is no such thing as a mean annual global person. Right? So I want everyone to recognize that when I say 10 degrees C changes in mean annual global temperature, that means that locally you can have very much larger changes and they can happen much faster. And that's where we live. Right? So that's an important consideration. The reason why I'm bringing up 10 here, Antonio, is that we tend to speak in terms of global averages. So when we talk about a 2 degree C increase in mean annual temperature as being a threshold for danger, that's a global average temperature that people are talking about, right? So we have to, when we talk about this subject, we have to speak both in terms of the global average, which is where, unfortunately, climate scientists are always pointing the finger, but we also have to recognize that we don't live on the global average, that where we live, you may have much larger temperature changes than that. You may have smaller temperature changes than that.
And I do want to talk a little bit more about this threshold for what's called dangerous warming.
Yeah.
In 1990, the United Nations Advisory Group on Greenhouse Gases advised in its warning that temperatures of 1 degree Celsius above the pre-industrial level may elicit rapid, unpredictable, and non-linear feedbacks causing extensive ecosystem damage. That's at 1 degree Celsius, not 2.
Right. Yeah. So a 1 degree Celsius temperature change on the planet is a large change. And by starting this conversation with 10 degrees C as the entire dynamic range between the warmest times 40, 50 million years ago, when it was so warm that there was no ice in Antarctica, to ice ages, when ice was pretty much taken over, much of the northern hemisphere. That 10 degrees C temperature change sets the bar, if you will. So when you're talking about a 1 degree temperature change in mean annual temperature, that's 10% of the large change that's happened over the last 40 million years. That is significant. And 2 degrees is 20% of that. So when we start talking about 1 to 2 degrees of temperature change, we're talking about very, very large, very impactful temperature changes. So keep in mind that when it was 4 degrees warmer, there was no land ice. When it was 6 degrees colder, there was no Canada, right? And so, the differences here are very large for small mean annual temperature changes.
Dr. William Norkhouse, he's an economist, a classical economist there at Yale, said in 1975 that beyond 2 degrees Celsius above the pre-industrial level would take us, in his words, quote unquote, outside the range of observations made over the last several thousand years, referring to the Holocene climate.
Yeah.
Outside of that range, it's just so coincidental that human civilization began to develop agriculture and went through the Neolithic revolution around the same time. When we talk about going above 2 degrees Celsius as a global average, are we talking about possibly losing the ability to grow food reliably?
It's a great question, and it's probably one of the most fundamental questions in what we call sustainability science. Just because it hasn't been that warm for the last 10,000 years doesn't mean it's not possible to grow food on a warmer planet. A warmer planet typically is a wetter planet, but that doesn't necessarily mean, when you have temperature and moisture, that doesn't make it. That's not the entire story for plants. Plants need CO2, they need nutrients, they need rain at the right times. You know, there's a whole bunch of caveats on top of that. And even more so for crops, which are specialized plants. Would it mean that we can't grow enough food? There's real question about that, particularly if population continues to go up. It is true, and I think this is probably not a coincidence, that, you know, human beings basically expanded out around the world and started, you know, agricultural revolution, etc., at a time when climate was pretty stable. For the last 10,000 years, climate has been really beneficially stable to human beings. And, you know, we shove it out of that comfort zone at our own risk.
And we are rapidly moving out of that zone. NASA clocked in 2016 at 1.3 degrees Celsius above the pre-industrial average.
Right.
The Intergovernmental Panel on Climate Change, in their fifth assessment, is projecting up to 4 degrees Celsius by the end of the century. My understanding is that the total impacts that we're looking at are not simply caused by general warming, but climate instability itself. In the United States, over our entire course of winter, we were seeing parts of the country having summertime temperatures, and then literally a week or two later, having extreme cold temperatures. North Carolina, for example, was rocketing from 70 degrees one week in February to 20 degrees just a week later.
Yeah.
The weather whiplashing effect.
Right. No, that's what you expect on a planet that's going through this kind of a change, because the tropics are warming up. There's a lot of heat down there, but you still have cold pooling up in the northern hemisphere in the wintertime and in the southern hemisphere in its wintertime. And that's because the sun, you know, you only get sun during the summertime up you know, in the high latitudes. And so it still gets cold. It doesn't get as cold as it used to get because there's too much greenhouse gas in the atmosphere to allow that to happen. But so there's a bunch of really interesting things that are happening right now. Because the temperature gradient between the equator and the poles is shrinking, cold air bottling, which goes on when you have a very large temperature gradient, doesn't happen so much anymore. So actually cold air is seeping out of or flowing out of the Arctic more often now, which is causing some of these yo-yos that you're talking about here, where you know, the east coast of the United States may be 70 degrees one week and 20 degrees the next week.
We saw temperatures as low as 25 degrees in Florida this winter.
Yeah. Yeah, the ability of cold air to stay up in the polar regions has been decreased by the decreasing temperature gradient. So, and this is what we're going to have to live through, right? We're in a situation now where, you know, a couple hundred years down the road, the Arctic is going to be so warm that you're not going to have so much of this ratcheting. But during this transition time between what was our old climate and what's going to be our new climate, we're going to go through some rather interesting, and I say that with a smile on my face, rather interesting times.
Dr. Jennifer Francis is the atmospheric scientist at Rutgers University right now, and she's leading the way in understanding what she calls jet stream sinuosity. Mm-hmm. Her conclusion is, as you say, as the gradient in temperature in the Arctic and the equator reaches some type of equilibrium or we're getting closer, that gradient is decreasing, that we are going to see more persistent weather patterns. And one of the examples that was given was Hurricane Harvey. We saw Hurricane Harvey, a Category 3 hurricane, stall over Houston for 5 days, dropping up to 50 inches of water.
Yeah.
Really historic.
Right.
Should we prepare and expect to have more storms, hurricanes stalling over the continental United States?
We've already seen an increase in the amount of rain per rain event. I think it's as much as 50 to 70% in some parts of the eastern U.S. And that's to be expected. When you have a warmer planet, you have more moisture in the atmosphere, and you have more opportunity for large rainfalls. And
My
that's,
understanding is that for every degree Celsius in temperature rise, we get about 5 to 7% more moisture into the atmosphere.
yeah.
Okay.
And that's a lot of water. And water doesn't come out, in a nice, even fashion. It comes out where cold air and warm air come together. So you have this combination of cold Arctic air seeping out more easily, meeting up with very warm, moist air. And yes, I mean, the answer is you get bigger rainfalls.
Okay. So, Dr. Jim White, as I was telling you earlier,
talking about here, Clinton, are pretty doggone simple. And we know what's coming. We know that the planet's going to get warmer. We just argue about how much warmer it's going to get. If you notice on any of these graphs, no one predicts it's going to get colder, or no one predicts no change at all. This is really, the arguments are over how hot is it going to get? And what's that going to mean in terms of sea level rise? And what's that going to mean in terms of refugees? And what's that going to mean in terms of food insecurity? And what's that going to mean in terms of fresh water insecurity? That's really what we argue about.
Well, I think this is a good segue for us to begin talking about sea level rise projections into the future.
And we're going to have to make that speedy. I'm sorry, because I've got to get off to another meeting here pretty soon.
Okay, no problem. Give me one. So here's a graph about projected sea level rise onto the future into 2100. The orange line or the red line that you can see there, that's the National Oceanic and Atmospheric Administration, NASA, predicting almost 3 feet or a meter sea level rise by 2060. And then you also have the Southeast Florida Regional Compact Climate Change projecting their sea level rises in the blue margin. But what you can see here, just for a little bit more information, the NOAA data is based off of the IPCC AR5 mid-range scenarios. That's RCP 4.5 and RCP 6.0 with a temperature range of 1.1C to 3.1C by 2100. And then you have your corresponding temperatures.
Yeah, this is, again, I'd make the same point with this graph as an initial point that I made with the temperature graph. No one's predicting sea level to stay level. Everyone predicts sea level going up. And really it's a question of how much it's going to go up. And, I would point out that the difference between, say, 3 feet and 6 feet by 2100 is, for many coastal cities, is kind of a moot point. Given the amount of infrastructure that exists within 3 feet of sea level rise, and I'm talking about electrical lines, gas lines, roads, etc., the sewer systems, the basic infrastructure of cities. If you raise sea level by 3 feet, Miami is not habitable. It costs you a ton of money, and it's not like people could just move up into refugia. Keep in mind that the toilets don't work anymore, and there's no fresh water, and the gas lines don't work. This is also true for Norfolk. It's true for, it's true for trillions of dollars of assets that we have along the coast. And one of the keys is we don't really know. First, we don't know how rapidly sea level is going to rise, and we don't know, but we do know it will rise. And we do know it's not a question of inches, it's a question of feet to meters. And note that this cuts off at 2100. You go out to 2200, 2300, 2400, and you're looking at, 30, 40 feet of sea level rise.
Well, presumably, as I say, the high-end scenario here is 3.1 degrees Celsius by 2100, and that's going to yield us 6 feet of sea level rise according to NOAA. But that's only if we stay at 3 degrees Celsius. But what you're saying is that beyond that point, these lines are pretty much showing us that they are on their way to that 20 to 40 meters.
Yeah, and I would point out that our understanding of how major ice sheets like Greenland and Antarctica respond to rapid temperature change is imperfect. We do know that the ice is melting. We do know that it's shedding into the ocean. But keep in mind that the ice sheets are not just some passive chunk of ice. We've got much of that ice with its feet below sea level, so it's metastable, fundamentally unstable. That ice could flow into the ocean much faster. It's really, the fundamental question is, how rapidly can ice go into the ocean? And that's still a question of scientific debate.
Dr. James Hansen, in his latest 2015 sea level rise and ice melt, is projecting 3 to 5 meters of sea level rise within a range to 50 to 150 years, with 2100 being the midpoint.
Yeah, I don't, as an ice core scientist, I have trouble with that volume of ice dumping into the ocean that rapidly. If you look at the history of sea level rise in the past, 3 meters over a century is certainly possible. It's happened before. 5 meters over a century is about the maximum that we witness, that we see. But certainly 3 meters over a century is possible. But that's back when there was a lot more ice available to be dumping into the ocean. That being said, you know, I won't be around, but it would not surprise me if that indeed was the result. Because again, our understanding of these large ice sheets is imperfect. I wouldn't bet on it going up that fast, but you know, this is not a betting matter. You know, the amount of damage that will be done by just a meter of sea level rise is really tragic. We're going to have to go.
Okay. Well, thank you so much, Dr. Jim White, for being with us today, talking about global average temperature rise and sea level throughout the rest of the century.
And Clinton, my apologies for calling you the wrong name earlier. That was my fault. My apologies.